Welcome to part 22 of the lecture on catalytic organometallics. Well, let's have a look at the group 10 metals. That's nickel, palladium, and platinum. And as you certainly remember, we spent a lot of time in discussing palladium catalyzed reactions. Certainly, palladium catalysis offers the richest and most versatile catalytic systems. So, most versatile, a rich catalytic chemistry. What about platinum? Well, we discussed some platinum catalyzed reaction in connection or in comparison with gold catalyzed processes. However, platinum carbon bonds are known to be significantly more stable than palladium carbon bonds, and more stable carbon metal bonds means slower in catalytic processes. So, it is useful in special cases, but compared to palladium chemistry, it does not really compete. Well, what about nickel? So, nickel was known to be less active. Generally, you need a higher catalyst loading, well, in the range of 3 to 20% catalyst loading. And as you know, with palladium chemistry, we normally start our test reactions with 5 to 10% palladium. On the other hand, later on, one tries to optimize until maybe 0.001% palladium. However, as we will see later on, nickel can be far more active in certain cases than palladium. And, of course, nickel has a very simple advantage. It is much cheaper. So, palladium acetate is 300 times more expensive than nickel acetate. And this is certainly an important argument for applications in industry. Well, therefore, let's start with nickel catalyzed reactions in industry. First of all, the well-known DuPont adiponitrile process. So, it's about the synthesis of adiponitrile, and you start with butadiene. With adding HCN to the butadiene, catalytically with a nickel catalyst. So, HCN, butadiene, and the nickel catalyst will give a nickel allyl, pi allyl complex. Two ligands at nickel, cyano group here. So, and in an equilibrium process, either this branched nitrile is formed, or the linear one, usually in the range 1 to 2, since these are reversible processes, you can isomerize this one to that one. In addition, it is possible to isomerize that one in the presence of an additional Lewis acid. So again, HCN, zinc chloride, and a nickel catalyst, usually a nickel phosphine or a nickel phosphide catalyst, to a product with a terminal olefin, which then can undergo a hydrocyanation reaction, again a second hydrocyanation, forming the final product, the adiponitrile. So this is an important starting material for polymer synthesis. For instance, reducing that, hydrogenating it for the to get to the bis amino compound, and so on. Well, the hydrocyanation has also been tried in the last 20 years to perform that enantioselectively. selectively. The first example, already from 1979, the group of Elms, well, used in that case palladium diop complex. Diop is a chiral bidentate phosphine ligand we already discussed. But low enantioselectivity. However, to my knowledge, best example is from 1995, a group of Rajan Babu, and he applied nickel catalysis nickel COD, cyclooctadiene ligand, HCN, hexane, room temperature, a chiral phosphide, ligand, and well, the best result for better 90% EE was, yeah, well, he achieved better than 90% EE, and you might imagine in which context this reaction was done. Well, we already discussed some examples of that anti-inflammatory drug. Naproxen was the name. Well, problem is the low turnover number, well, relatively low for an industrial process. Turnover number is less than 750. Well, now to some nickel catalyzed processes which are indeed relevant for industrial applications with high turnovers. One of the first was developed by Walter Reppe. He was chemist at the BASF, and well, the expression Reppe chemistry is well known in industry also today, nowadays. So, important industrial processes like to start from cheap starting materials. Ethylene, carbon monoxide, and water. So a nickel carbonyl catalyst about 200 bar pressure, 300 degrees as temperature, will lead to propionic acid. Still one of the important processes for the synthesis of that. And here you can see how versatile also nickel chemistry can be. Essentially the same process, but starting from acetylene. Well, nickel bromide and a copper halide as the co-catalyst. 50 bar, lower temperature, 200 degrees, and this is a nice process for the production of acrylic acid. Also, under the label of Reppe chemistry, is this process. Acetylene, nickel cyanide, calcium carbide, THF 60 degrees, 15 bars pressure. Well, on first glimpse one could guess that benzene is formed. Well, benzene, the cyclotrimerization of acetylene we discussed yesterday, is a byproduct of that type of reaction, but you can trigger that process that indeed the cyclooctatetraene is formed in up to 90% yield. Not for industrial purposes, but for lab scientific purposes. This reaction has been modified also with this starting material. 2 equivalents, 2 units of that, are cyclized with a nickel catalyst to the cyclo-octa tetraene moiety E is the abbreviation for ester here. And of course, all of you should know that the cyclooctatetraene is not an anti-aromatic system, because for being anti-aromatic it should be planar, but it is not. Okay? Some kind of boat-like conformer is formed. So, this was 90%, okay. 89% are reported in that case. If they would optimize it, they would also get 90%, I would guess. Well, okay. Rather similar, since also an 8-membered ring is formed, is the dimerization of butadiene. Forming this 1,5-cyclooctadiene, which is, this is this COD ligand we already talked about. And depending on the reaction conditions, also a cyclotrimerization can be achieved. Mainly to that trans-cis isomer. So these reactions have been developed also by Reppel, to my knowledge, originally with nickel catalyst. Nowadays the industrial process is frequently based on the titanium aluminum combination with regard to the Ziegler-Natter catalysts. However, a nickel catalyst is normally applied for the hydrogenation reaction, the last step. Finally forming this cyclododecane. So what are these good for? Well, you can selectively monooxygenate that, forming the cyclododecanone. Well, this might be interesting for perfumery, On the other hand, Baeyer-Williger oxidation will form a macrocyclic lactone. You can open that up for polymer synthesis or for some special kind of fatty acids. Well, interesting materials for industrial purposes. For this type of cyclization, 4+4 cyclization, there are also interesting examples from academics. Paul Wender in 1988, at that time already at Stanford University, performed that 4+4 cycloaddition reaction intramolecularly. In the context of a natural product synthesis with nickel COD, triphenylphosphine. Oh well, okay. You can try to figure out what will be that cyclization product. It's not that difficult. This one with a 67% yield, while all those hydrogens at the stereogenic centers are on the same side of that ring system. And also from Paul Wender's group, is a 2+4 cycloaddition reaction, again intramolecularly. Again, nickel COD, and well, the ligand then had to be optimized, a phosphide reaction conditions, toluene just at room temperatures 25 degrees. So as I said, it's just a 2+4 cycloaddition reaction. Which one, of course, can call a Diels-Alder reaction. Excellent yield, 98%. Well, but it is not a normal Diels-Alder reaction. In a normal Diels-Alder reaction, you have an electron-rich diene and an electron-poor dienophile. If you have a Diels-Alder reaction with inverse electron demand, yeah, then it's the opposite. But here, in this case, electron-rich diene and an especially electron-rich TMS acetylene. This does not react at room temperature at all. although it's an intramolecular setup. You need that catalytic system for the reaction to proceed. I already mentioned the Ziegler Natta catalysts. Well, Ziegler Natta catalyst are known for the polymerization of olefins, mainly ethylene and propylene, at lower pressure and lower temperature. So, polyethylene is produced. So, and already Ziegler at the Max Planck Institute for Kohlenforschung in Mülheim found that nickel impurities, the presence of nickel impurities, which, well, just came from the autoclave, the steel of the autoclave, and there is some nickel in there, of course. Yeah. In the presence of nickel impurities, that reaction of ethylene with itself stops already at the stage of a dimer. This means only 2 units of that react when it stops at the stage of 1 butene. Well, this might be also useful. And most interestingly, in recent years, some industrially oriented research groups tested this type of process for enantioselective catalysis, combining styrene plus ethylene, 0.01% of a chiral nickel catalyst, amido phosphide as ligand. I think we have seen that one as ligand before in the course of this lecture. So, what a huge setup for synthesizing such a small chiral molecule. This one. Well, about 89% yield, 91% EE. Well, there are some examples with a higher yield and somewhat higher enantioselectivity. However, with a higher catalyst loading, this reaction was found by Walter Leitner, who also was a couple of years at the Max Planck Institute for Kohlenforschung and is now professor at Aachen University. So, what else is on the list of nickel catalysis? We have mentioned nickel catalysis before in the context of the Kumada coupling process. What was the Kumada coupling? Well, essentially, you have a Grignard so, and R might be alkyl, aryl, or vinyl. Then you have a vinyl or aryl halide so R prime, generally vinyl or aryl. The leaving group, chloride, bromide, iodide, triflate, and in some examples even fluoride. And with palladium catalyst or nickel catalyst, you get the C-C coupling product. Some extension of Kumada coupling where you can combine sp3-centered carbon atoms with each other have been invented in recent years, but then based on nickel catalysis. For instance, N-octyl chloride combined with N-butyl magnesium halide gives, well, this is dodecane, but consequently I write it that way, N-octyl combined with N-butyl, 96% yield. This is achieved with 3% nickel chloride, THF, 25 degrees, and what is essential, you need the presence of a butadiene. That might be the parent butadiene, but it can also be isoprene. It is essential, and those nickel butadienyl complexes, well, it is rather complicated. With rather complicated structure, there's already a CC bond formed between two of those butadiene units, while there's lots of details we don't need to discuss. What is more interesting for us is that this type of process or similar process has also been applied for enantioselective CC bond formation. Here we have a very nice example. an alpha bromoamide which is a chiral compound that was applied in this reaction as racemic mixture. The organometallic reagent, in this case not a Grignard, but an N-hexyl zinc bromide. Nickel chloride as the catalyst, and the pi box ligand. Delivered the chiral information. So, you achieve the synthesis of the enantioselectively enriched product. %90 yield and 96% EE. That means that the chiral center is epimerized during that reaction. During the reaction there is then, in some stage, no chiral center, and all the chiral information then comes from the pi box nickel complex. 90% yield, 96% EE means that, well, even the wrong enantiomer here gives the right one there. Okay. So, further interesting reactions with are based on nickel catalysis. Well, let's have a look at the nickel catalyzed Suzuki coupling reaction, which becomes more and more important in recent years. So, examples. Well, the nickel catalyzed Suzuki coupling is especially successful with chloroarenes, which tend to be less active in palladium catalyzed processes. So, with 10% of nickel chloride with a DPPF ligand, the biaryl product is obtained with 94% yield, whereas with the corresponding palladium complex you get less than 1% yield. And a very nice example of a stepwise Suzuki coupling was published in 2008 in the Journal of the American Chemical Society on page 14,422. Neil Garg's group at the UCLA. So, it's worth having a look into that publication. A pivalulyl group here. So what is pivalulyl? That is this tertiary butyl substituted ester there. Bromide on this side, pivalulyl here. First step, with this indole substituted boronic acid ester, and with triphenylphosphine as the catalyst. Potassium phosphate as the base, toluene, a bit of water in there, 90 degrees, and the normal Suzuki coupling product was obtained. Sorry. I forgot there is anylated benzene ring. So this is the normal coupling product as anticipated. Yield 90%. And now to the fascinating, interesting, very valuable part. Well, this is also valuable, Suzuki coupling, it's clear. Next step. A nickel catalyst based on a nickel chloride phosphine, tris-cyclohexyl phosphine complex. 5% of that. All the other reaction conditions the same, except temperature, also toluene a solvent, temperature was 110 degrees. And that simple boronic acid, phenyl boronic acid, as the coupling component, then indeed this pivalulyl group is the one who reacts within that nickel catalyzed Suzuki coupling. The CO bond is broken. And I think this is remarkable. You can start from a phenol making the pivalulylic acid ester, and then performing that nickel catalyzed Suzuki coupling. So, this is the result, and for the last step, 88% yield. As I said, quite remarkable. So two more nickel catalyzed processes. One is already a name reaction, Nozaki-Hiyama-Kishi reaction. Sometimes abbreviated as NHK reaction. So, what is that? Essentially, you have a vinyl or an alyl halide, then an aldehyde, you need, for the Nozaki-Hiyama-Kishi reaction, chromium chloride, unfortunately in excess, a nickel catalyst, then sometimes rather complicate ligands, which can be chiral. You need strong base, a proton spun, solvent. And what you get then is an alcohol. What reminds us of simple Grignard process. 1,2 addition of an organometallic species to an aldehyde. So, when are you using the NHK, special NHK process? Well, in cases where you need an especially high selectivity for the 1,2 process, which also works for alpha-beta unsaturated carbonyl groups, when you need a functional group tolerance. For instance, ketones, esters, amides, and nitriles are tolerated, even a solvent. You can't do that with a Grignard, for instance. You can achieve high selectivity for the process. Well, is one example for real complicated setup of R prime and R, and you achieve 100% yield that was developed in the context of Kishi's polytoxin synthesis that complicate natural product with 64 stereogenic centers, as you might remember. Yeah? And then you can also achieve that with an extremely high diastereo selectivity. So, if you have worked maybe 1 year synthesizing this one with a complicated setup, and another year for another guy, another year with that and a complicated R prime there, and you want to go sure that you get a good yield out of the process, you know, well, okay, the Nozaki-Hiyama-Kishi process might be the process of choice, okay? So, another interesting process well, recently invented, it's a nickel catalyzed reductive coupling of alkynes. So, R and R prime can be aryl, alkyl, and it can even be just hydrogen. Also terminal alkynes. Then an aldehyde nickel COD additional ligand, some reducing agent. So the ligand, for instance, an butylphosphine, and a reducing agent often applied is this borane. Then the coupling process finally leads to this result, an allylic alcohol. So a reductive combination with CC bond formation of an alkyne and an aldehyde. So for the mechanism of the process, the nickel complex coordinates both the alkyne and the aldehyde. Forming a metallar cycle like this. The reaction then with the triethyl borane will lead to this intermediate, so, and now a beta hydrogen elimination can take place. Ethylene is set free. Well, and now no problem. Reductive elimination. Forming the carbon-hydrogen bond. Again, the active catalyst. And I'm now not quite sure is this one hydrolyzed later on, or maybe it doesn't survive the reaction conditions. Later on, you have the alcohol here. Well, one example. Benzaldehyde and the terminal octene gave this allylic alcohol with a yield of better 75% and 96% of the E-olefin. As I said, a rather new development, if you want to look that up in literature. Again, in the Journal of the American Chemical Society, 2011, page 5728. I think that's enough for today. Thank you for listening. Have a nice holiday tomorrow and see you next week.